right now. Okay. With my great pleasure, let me introduce our next talk today, Professor Volodymyr Nekrashevych from Texas A&M University, which will tell us about topological and conformal dimension of self-similar groups.
Дуже дякую. Чути мене?
Так.
Я не можу share. I cannot share the screen while other participants is sharing.
No, you can. You will try one more.
Окей, дякую. Дуже радий взяти участь. Сподіваюсь, наступного разу живу. So, I hope you can see my screen. Can you?
You can use full screen if you don't mind. It will be better. Control L.
Yeah, I know, but then I cannot mark it. Okay, I'll try.
Okay, okay. Or view full screen.
Yeah, I know.
Mm-hmm. Okay.
But then I will use. Okay. So I'll talk about topological and conformal dimensions of self-similar groups. Fortunately, Professor Nekrashevych has defined a lot what I need, but I'll still go through the definitions. So, what are self-similar groups, especially since there are some differences in my and Professor Nekrashevych's definition. So, what are self-similar groups? Let X be a finite alphabet, and the faithful action of a group on the set of finite words over this alphabet is called self-similar if for every group element and every well, I want word. So every word V, there exists another group element, which I will denote G restricted to V, such that if you apply G to words starting with V, the result is first you apply G to V, and then this new element to the remainder of the word, the tail, for all words W. So the same definition as in the previous talk. Differences in the previous talk, V was a letter, but then if you apply the definition several times, you will get the same definition, but for words and letters. And this is called section or restriction. And you can extend this definition to infinite words. So every action on finite words gives associated action on the right infinite words, because as you see, the action on prefix is done by the same element. So when you write infinite words, it will extend. And this action will be also called self-similar action. More generally, actually, I would like to consider also non-faithful self-similar groups. So that was also basically defined in the previous talk, except for one little detail. We have an action, not necessarily faithful, so some elements may act identically. And we have a rule, the section map, which for every group element and every word gives you a group element, satisfying these conditions. Well, equivalently, probably more natural, this is nothing else but a homomorphism from the group into the Reed product. A symmetric group, so semi-direct product of symmetric group with direct power of G labeled by X. So that was also mentioned in Sarvanech's talk. The only difference is that he insisted that this is injective. I don't require it to be injective. It can be any homomorphism. So I also call these homomorphisms, so similar groups. Definition, some similar action in the first or second definition is called contracting if there is a finite set of group elements, which we'll call the nucleus, such that if you take any group element, there exists an n, such that all these sections, so restrictions to tails, restrictions to suffixes, are in the nucleus for all words of length n or more. So in other words, in terms of groups acting on rooted trees, it means that there is some finite set of patterns, some finite set of group elements, such that if you take any element of the group acting on the tree, then starting from some level, if you look at the subtrees that grow from that level, inside the subtree, you see only action given by these finite elements of this finite set. So you see only finitely many possibilities if you look deep enough. An equivalent definition, which I will mention a little bit later, is that this section map contracts the length of group elements. So G restricted to D is shorter than G, is simpler than G. So we will see this interpretation a little bit later. An example, the very classical prototypical example is the so-called adding machine. That's an action of the cyclic group generated by one element A, and that acts on the binary alphabet, 0, 1 alphabet, by the rule that if the word starts with 0, you change it to 1. If it starts with 1, you change 1 to 0, but then act by A to become the A. So that's exactly how you add 1 to a binary integer, except for you write this binary integer the opposite way. So you change 0 to 1 when you add 1. If you see 1, you change 1 to 0 and then carry. So add 1 to the remainder of the word. So this is contracting with nucleus 1A or A inverse. So when you add or subtract, eventually when you start doing it, you will carry 1 or negative 1. You will not carry anything. Here is another definition. So when you see A, A acts basically like the adding machine, except for here you have B instead of A. And then B doesn't change the first letter, and then act by A on the remainder of the word if the word starts with 1. So we can look at this as a recursive definition of the action. So now if you know this formula, you know how to change the first letter, then you know how to change the second letter, third letter, and so on. So this will define action of A and B on words, finite or infinite. But you also can look at this as at a homomorphism from the free group generated by AB to the semi-direct product. So A flips 0 and 1. That's the element of the symmetric group. And then at coordinate 0, you have identity. At coordinate 1, you have D. So that's an element of the power. So you have this group G, which is for now a free group. So this is element of F squared. So this is an element of the semi-direct product, where S2 acts on the coordinates naturally by permutations. So this gives you a homomorphism. The first line tells you where A goes to, the second line tells you where D goes to. D goes to identity as an element of the symmetric group, and then 1, A as an element of the F square. Well, sorry, let's call this F square. So there are two ways of looking at it: as a definition of an action. Then you have a group of automorphisms of the tree, a faithful action, or you can look at this just as a homomorphism from the tree group to the real product. So first one is faithful self-similar group. The other one is just self-similar group, not necessarily faithful. It's interesting that this is already contracting for the free group. So if you look at this as a definition of as a homomorphism for the free group, if you start applying this homomorphism over and over again, eventually the elements that you get in the coordinates are elements of this finite set. So this is contracting also for the free. If it is contracting for the free group, of course, this also implies that it's contracting as a phase action. Okay, so limit dynamical system. So Rustam mentioned Schreier graphs, finite Schreier graphs on the levels of the tree. So these limit spaces are in some way limits of these Schreier graphs. So the formal quick definition is as follows. Suppose you have a contracting group. Consider now the topological space of left infinite sequence. So the group acts on the right infinite sequences, but we are looking at the left infinite sequences infinite to the left. And then consider the equivalence relation that you identify two left infinite sequences if and only if there exists a bounded sequence of group elements. Bounded means that its set of values is inside a finite set, such that it moves the suffixes of the first sequence to the suffix of the second. So moves the ending of length n of the first sequence to the ending of length n of the second. So in other words, the endings are on bounded distance with respect to the action of the group. And then let's take the quotient of the this topological space with a direct product topology by this equivalence relation. So this quotient is the limit space. Now this dynamical system is invariant under the shift. So the shift preserves the equivalence classes. So we get a continuous map on the limit space. And this limit space together with this map is called the limit dynamical system. There is an opposite operation where you can reconstruct actually the group G from the limit dynamical system, except for you have to add some finite information. So J in general, it's not a topological space, it's an orbit space. So you need to equip it with a little bit more information than just topological space. But in many cases, it's just topological space. In many cases, this orbit space structure is trivial. And then the group G is the iterated monodromy group of this limit dynamical system. So we have we can go back and forth. In a way, the two theories are equivalent. Theory of contracting so similar groups and theory of expanding, locally expanding covering maps of orbit spaces. So I don't have time to write the opposite direction. I just want you to remember that iterated monodromy groups and still similar groups, contracting so similar groups, can be thought of as an algebraic theory of some class of dynamical systems. There is a bijection between some natural equivalence classes of so similar groups and equivalence classes of these expanding maps. Because there is this equivalence, because there is this relation between one class of object and the other class of object, it's natural to try to understand how properties of one object are related to properties of the other. So on one side, we have groups. So we have some algebraic properties. On the other side, we have topological spaces and dynamical systems. So there are some topological or geometric properties. So how topological properties are related to group theoretic properties. That's a classical subject of basic group theory or topology. So one of the most basic notions in topology is the topological dimension. So I don't think I have time to define it. So it is technically what I'm using is the house of covering dimension, but because these limit spaces are very nice topological spaces, they are metrizable, compact. Any classical definition of topological dimension will work and will give the same number. So let G be a contracting self-similar group with nucleus N and limit space J. Then the following conditions are equivalent. Dimension is less or equal to D. And the second condition is purely algebraic. It says that there is some level N of the tree. So, and you can partition so that you can partition it into D+1 sets. Sorry, not N, D+1 here. Such that if you take the isomorphism, let me draw a picture. You have these subtrees. So these are subtrees of words starting with a given letter. So you have this level N. So there are these words, and you look at words starting with it, starting with them. And then you take the elements of the nucleus and look how these elements, as automorphism of the whole tree, act on these subtrees. So they will map one subtree to another subtree, then again another subtree. So there will be some isomorphism between subtrees. Now you cut this tree into these subsets. So now you look only at isomorphisms induced by elements of N, which move a subtree in one of these sets to the subtree of the same set. So you have some set. So you have some colors. You color this X to the N into D+1 colors. And you look only at the isomorphisms between subtrees of the same color that are induced by elements of the nucleus. So for each I, you get some finite collection of subtrees, and there will be some isomorphisms between subtrees. Maybe there will be very few of them. Maybe there are only the identity. Identity is always in the nucleus. Maybe there is only identity. But maybe some elements of the nucleus move subtree to subtree of the same color. So you take all these isomorphisms and then take all their compositions. So if you have one isomorphism going from here to here and another from here to here, you take their composition. So the condition is that this way you'll get only finitely many isomorphisms. Because if you take all of them without coloring, you get the whole group G. So that will be definitely infinite. But the condition that you can cut it in such a way that in each color you have only finitely many isomorphisms. So that's the combinatorial description of the topological dimension. So the smallest D satisfying this condition will be the topological dimension. It's not very constructive because it gives only upper bound on topology, but sometimes you can get also lower bound using different methods. So some applications. Or some additional theorems. So we have faithful contracting self-similar group. Let G, I use J usually. J be the limit space. Then, first of all, zero dimension means basically that G is finite. And more generally, it's if and only if G is locally finite. So every finite generating set, finite set generates a finite group. Equivalently, the nucleus generates a finite. So that's kind of non-interesting. Dimension 1 also has an algebraic characterization. The limit space has dimension 1 if and only if there exists a virtually free contracting group, such that G is its faithful quotient. So there is a Reith recursion for a virtually free group. So there is a homomorphism from F from some virtually free group to the Reith product of the symmetric group with that virtually free group, like I mentioned, like I gave at the beginning, and it must be contracting, so it will define an action on the tree. So this group G is the faithful quotient, so the group of automorphisms of the tree coming from this recursion. So to be finite dimension, dimension 1 is equivalent to the condition to be contracting on a virtually free group. This gives some. You can use this theorem and the result of Grigorchuk, Benli, and Delar to prove the following classification of finitely presented one-dimensional group. So if you have a contracting, self-replicating, that's a technical condition which is a little bit stronger than self-similar. With one-dimensional limit space, then the group is either finitely presented, sorry, infinitely presented, so there is no finite presentation, or is isomorphic to infinite cyclic group or to the infinite dihedral group. In fact, for non-self-replicating, it must be virtually abelian, but that's it's an open question if finitely presented contracting groups are all virtually important. But you see that here we have a very strong confirmation of this for dimension 1. I should say that all examples that were studied so far are very strongly one-dimensional. So 2 dimensions and higher is totally uncharted area. We don't know almost anything about them, except for some few examples. But there are many. Okay, so for example, the group that I mentioned before, generated by A and B, I mentioned that it is contracting on the free group as a free group. So it has one-dimensional limit space, and it's not cyclic. That's virtually cyclic. So in fact, it has exponential growth. That immediately from that theorem implies that this group is infinitely present. And here are the Schreier graphs, so the graphs of the action on the finite level. So that's on the first level. A is red, so H interchanges A and B, so these are loops. So there are 2 vertices only, this vertex, this and this. This is second level, third level, fourth level, fifth, sixth. And you see that it kind of converges to this. And this is topologically one-dimensional. And you take any of the definitions of topology and you can easily see that it's one-dimensional. This is the basilica. And so that group is the basilica group, and I also mentioned in the previous talk. Okay, another characterization, which I also don't have time to define all the notions. So if you have but I want to mention it, if you have a self-similar group action, you have, as I mentioned, associated actions on infinite words, so on the boundary of the tree, and you connect one point with another if one is image of the other by the action of a generator. So if you restrict this to an orbit, you get a connected graph, which is orbital Schreier graph. So the talk of Professor Grigorchuk was about spectra of these graphs precisely. The topological dimension theorem, topological dimension of the limit space is equal to the Gromov asymptotic dimension of the orbital graphs of its action on the boundary. So there is an analog of topological dimension for large-scale structures, and so we have exact equality between topological dimension of the limit space and asymptotic dimension of the orbital graphs. So this group theory and topology in this way are kind of dual in a way, in some sense. Okay, so now in the remaining time, I want to talk about geometry, not topology. So first, I'll give another definition of contracting group, which explains why it's called contracting. Again, let's have a finitely generated infinite self-similar group, not necessarily faithful. And so consider the classical LP norm on the vectors. And also I include infinity. So in the infinity case, this is maximum of the absolute value of the coordinate. And then LP contraction coefficient of the group, of the self-similar group, is the following number. So you take level n, and then you take all the sections on that level n, so in the words of length n, and take the lengths of these sections. So we have it's finitely generated, so there is some finite generating set, and so every element written as a product of generators has some length. So you take these lengths, so you get some natural numbers. You get p to the n, so size of the alphabet to the n natural numbers. That's a vector. You take the LP norm of that vector and divide by length of G. So you compare the LP norm of the length of sections to the norm, to the length of G. So what is the ratio? Take this ratio. Take lim sup as the length of G goes to infinity. So take the worst case, the largest case scenario at infinity. And then take nth root of this, limit as you take nth root of this. So this will give you the rate by which the length is contracted in the sense of LP norm. The length of group elements is contracted in the sense of LP norm. In fact, you can take limit here, not lim sup. But this is the LP. So for every P, including infinity, you get this number. And this number will not depend on the generating set. And to be contracting is equivalent to have to be P in contracting at infinity. So eta infinity less than 1 is the same as contracting. So that's another definition of contracting. Eta infinity is less than 1. So suppose that this is a contracting group. This function is non-increasing for any group, not necessarily contracting. For any group, it's non-increasing and continuous, actually. And contracting is the same as eta infinity less than 1. So there will exist, so you take the infimum of the set of values P for which eta P is less than 1. So this set will be some interval from either closed or open half line from PC to plus infinity, and you take the end of that half line. It can be closed or open, so it might eta P might be less than 1. Actually, no, because it's continuous. We call it the critical exponent of the group. So this is a sort of measure of complexity of the group. In fact, so there's, I didn't write this down, but that's an interesting fact. So if you take a group element and start looking at the sections, so find sections on the first level or third level, but each time you stop whenever, as soon as the element is in the nucleus. So when you find an element of the nucleus, you stop there and do not grow the tree. So at the end, you'll get some finite tree where the leaves are the words where for the first time you got an element of the nucleus. So the size of this tree, the number of vertices in this tree, is roughly length of G raised to critical exponent. So this is a measure of this critical exponent is a measure of complexity. How complicated are these group elements in terms of length of G? Okay, so now another a counterpart of this number in the sense of for the limit space. So let's take the limit dynamical system or the limit space. So I remind you that the limit space is the quotient of the space of right infinite sequences. And this set of right infinite sequences, because we have direct product topology, it has a natural set of basis of topology consisting of sets with a given sequences with a given ending. So if you take some word of length n, this will be a closed and open set in this space of infinite sequences. And the longer is n, the smaller is this set. So you get kind of a sequence of partitions, of fine and finer partitions as n increases, and these partitions converge to singletons. Now, J is the quotient of this, so there's a continuous surjective map. So these sets will be mapped to some closed subsets of J, some compact subsets of J, and for every n they cover J. So we get for every n some nice covering of J by closed sets, some kind of tiling. Tiling they may overlap, but for example, for the adding machine, this is just a partition of the circle, which is the limit space of adding machine, by binary segments. So we get these tilings, these tiles. So they're images of these sets under the quotient map. So for every point of the space and for every n, take denote by t psi of n, the union of these tiles, of these images of these sets of length t given to n that contain psi. So you get a tiling of level n, and for point psi, you take union of those tiles. So for example, for the circle, say level n, you cover the circle by intervals of length 2 to the minus n. And if the point is interior point of this segment, then this t psi n is this segment. Actually, sorry, that's wrong. You take not the union of images that contain psi, but also take those and intersect them. So you take images of tiles, you take tiles that contain psi, but then also take tiles that intersect those tiles that contain psi. So if you take a point, you take this interval, but also you take both neighbors of this interval. You take this set. If you take this set, you take these two tiles because they contain it, and then all those that intersect it. So you take this. So for the circle, this set will be of size either 3 times 2 to the minus n or 4 times 2 to the minus n. Sorry, this is not correct. Not only union of these sets, but also those that intersect them. Sorry. Okay, so this will be some kind of neighborhood of psi of level n, and consider all metrics on the limit space, which there is a measure on the limit space, such that first of all, if you take any of these neighborhoods, then they are between two circles with respect to that metric, such that ratio to disks, to balls, with a center in psi, such that the ratio of the radii is less than c. In other words, this set must be approximately round. And the second condition, that the volume of the ball with respect to this measure is r to alpha up to some constant. So this calls Alfor's regularity. Then alpha is the Hausdorff dimension of this metric. And the set AR is actually non-empty, so there is some class of metrics which always work, and measure is just Bernoulli, uniform Bernoulli measure. But there are many more. And for example, if you have post-correctly finite rational function, then if complex rational function, then you restrict the usual metric on the sphere to the Julia set, then that belongs to this class for the iterative modular group of iteration. Definition: the Alfor's regular conformal dimension of the Sumy group is the infimum of the Hausdorff dimensions of this matrix in this class. So it's infimum of these alphas that appear in the second position. So this is a more this is always, because it's infimum of Hausdorff dimensions, it's not less than the topological dimension which I mentioned before. So first theorem is that post-critical exponent, the critical exponent which I defined before, is bounded above by the Hausdorff dimension. So in particular, this conformal dimension, it bounds complexity of the word problem, for example. So in this way, you can prove that so for every epsilon, there is a word algorithm that solves the word problem with complexity conformal dimension plus x. This is in general, it's a strict inequality. For example, for the Grigor-Chuk group, this is less than 1, so the formal dimension is equal to 1. But for many examples, we have equality, and it's a kind of a mystery when we have equality, when it is strict. So I mentioned that. Okay, so I must keep this, I guess, or maybe I'll return to it later. I want to formulate the full theorem. So let's consider a probability measure on the group G. Since G is discrete, it's just the same as saying that you take a function, positive function on G such that the sum of values of the function is equal to 1. We get then the associated random walk. So we start from identity and then multiply by group elements. So we get S1, S1, S2, S1, S2, S3, and so on, where Si are independent and distributed according to mu. So you jump using Si with probability mu of Si. Poisson boundary of the random walk is the quotient of the space of trajectories by the measurable half, so the smallest measurable equivalence relation. which identifies any two trajectories which have the same future. So starting from some moment, they are the same, maybe shifted time. So if you identify any two trajectories which have the same future and take the quotient in the measure theoretic sense, then you get the Poisson boundary. And mu is Liouville if the Poisson boundary is trivial. So in other words, there are no events at infinity, no measurable events at infinity, which are invariant under this relation. So if the measure is symmetric and its support generates G, then this property implies amenability of the loop. So the following theorem is joint result with Mattebon and Zheng. Suppose you have finitely generated contracting loops with conformal dimensions strictly less than 2. Then for every symmetric measure with finite t moment, so you integrate a length of group elements raised to t with respect to the measure and require this to be finite for some t greater than the critical exponent. So for example, for p equal to 2, so second moment is finite, that's enough. Then this measure is Liouville. In particular, the group will be amenable, and that's a big deal for us. In particular, yes, this implies amenability of the group. You can take the, for example, the uniform measure on the finite generating set. That will definitely have finite moment. Corollary for holomorphic dynamics: let f be a positively finite complex rational function such that its Julia set is not the whole sphere. Then the iterated modular group is amenable. It's an open question if it is true for all contractings. And this is a big step, I think. Well, maybe not big, it's only up to dimension 2. But we didn't have even that. So here are some examples. Here is the iterated modular group of this rational function. This is an example where we knew before that it is amenable, because if you look at the automaton generating it, this group, you see that there are 2 isolated cycles. I mean, only 2 cycles, and there's a path from one to the other. All the other arrows go to the identity. Remove that. This is an example of something called polynomial activity growth. And for those we knew that, that it is amenable, we didn't know that it is Liouville. And this kind of examples have topological, have conformal dimension 1. So this has conformal dimension 1, even though it doesn't look like. So here amenability can be proved using something called extensive amenable actions due to Yushchenko and Monod, essentially. Here is another example. In this case, the Julia set is homomorphic to Sierpinski carpet. So here the conformal dimension is strictly greater than 1. We have some lower bounds, but we don't know what it is. It is between 1 and 2. It's not 2 because obviously it's a plane. And here is the group whose limit space is the classical Sierpinski carpet. It's also house of, therefore, conformal dimension strictly less than 2. By the way, nobody knows what is the conformal dimension of the classical Sierpinski carpet. But there are only some numerical estimates. It's less than, it's strictly less than the obvious Hausdorff dimension of this. So it's less than log log 8 over log 3. But there are some lower bounds, but nobody knows what it is. But for us, it's not important. For us, it's important that it's less than 2. So this group is Liouville and therefore amenable. And we don't know any other proof that it's amenable. This is the only proof that we have at the moment. Okay, thank you very much. That's all what I wanted to talk about.